Anne-Catherine Rieu. I'm the plant manager of Motores, one of the biggest mechanical plants of Renault. Motores plant today is representing 1.5 million engines a year. So this is 40% of the global engine production for Renault.
El mayor reto, el mayor challenge que tenemos es el aumento de las exigencias de calidad continua que se autoexige Renault para que sus piezas tengan cada vez mayor calidad. Para lograr los retos que se nos presentan, necesitamos un proveedor que mire más allá, no solo que mire el líquido, los parámetros, la calidad, sino que mire también, por ejemplo, los sistemas. Y ese proveedor lo hemos encontrado en Castrol.
Renault and Castrol has a very good partnership just because we share the same future. We have the same values and behaviors, starting with safety, quality, performance.
Castrol me ayuda a conseguir los objetivos esperados mediante su tecnología. Tiene productos de muy buena tecnología, su aporte técnico, su soporte en planta.
When we work with Renault, we try to put the best product, but not only the best product, the best technology and the best team inside to manage this combination of product, technology and process.
What are we looking for about lubricant suppliers? It's the most cost-effective product to go with very effective facilities with digital monitoring.
And this is clear the case of the XBD technology and XBC, the compatible cleaner. We understand that one of the needs that the customer has is this waste of water and cleaner.
Tenemos, por ejemplo, la tecnología XPB, sin boro o sin formaldehído. Tenemos también el Compatible Cleaner, es una tecnología muy importante de ahorro de consumo tanto de agua como disminución de los residuos.
With a great innovation from Castrol, we are able this year to save 1 million liters of water.
Mediante el cual ahorramos tanto en residuos con la disminución del impacto al medio ambiente como en ahorro de agua, el consumo de agua y ahorro incluso en productos.
And when we have this combination of coolant and compatible cleaner inside, we put another resources inside that is not only the team who manages this, we put the smart control that is a system that we can control 24/7 all the key parameters in the coolant and the cleaner. So it's the way that we close the cycle.
Tenemos el Smart Control, que podemos ver aquí, que es una tecnología de control de los parámetros de los líquidos en remoto y siempre intenta superarse e intentar conseguir nuevos retos, nuevos objetivos.
This is a real partnership. This is not a relation supplier-customer. The partnership with Castrol is very powerful because Castrol is not expecting the request from Renault, but is very proactive in the way of making new proposals, new innovation proposals.
Es un proveedor que entiende perfectamente nuestra filosofía, nuestras exigencias y que nos da exactamente lo que nosotros necesitamos.
Today we have new products with new innovation. We don't know exactly what will be the future, but we know that with Castrol partnership we can reach the sky. We can give the best cost-efficient products to our customer. We know that Castrol will bring us new digital innovation to follow the efficiency of the plant.
Good morning to all our participants in India and good afternoon to the NTU team in Singapore. On behalf of the Castrol India team, it is my pleasure to welcome you all
Recording
to the
in
third
progress.
and the last session of our 2021 edition of the Castrol Royalty Colloquium Program in conjunction with the prestigious Nanyang Technological University. To commence the proceeding, I would like to brief you on the statutory health and safety guidelines. Seated in a safe environment, we require attention to the moment. Be aware of your surroundings and avoid physical movements or any other distractions that may lead to potential incidents, example slips, trips, and falls. Hope you're seated comfortably in a safe position with a comfortable posture and back support. Keep ergonomics in mind and switch between positions to change your postures often. If you're attending this using a hand gadget, example smartphone, suggest place it on a desk or at a close distance from where we can comfortably watch during the event. Be relaxed at your desk and have refreshments or drink as required. Ensure that you stay hydrated. We request you to keep your microphone on mute unless the professor has requested you to speak or amidst the Q&A session during the training program. Alternatively, you can also write your questions in the meeting chat and we'll address to it during or at the end of the session. 75% attendance on all 3 days is mandatory in order to get a certificate from Nanyang Technological University, Singapore. I would request all the participants who've joined today using their smartphones or any other gadgets, please write your names and organization names in the meeting chat for us to rename you and mark your attendance. Let me now start this session with a quick introduction of our trainer for session 3 on industrial robotics, Dr. Z Ming. Dr. Ming has received his PhD degree from the University of Rennes, France in 1989. Since 1986, he has worked as a research assistant at ILSA and India Rennes, expert engineer at India Sofia Antipolis, senior lecturer and associate professor with the Nanyang Technological University. He was the general chair of 2007 International Conference on Climbing and Walking Robots, the general chair of 2009 International Conference on Intelligent Robotics and Applications, the co-founder of International Journal of Humanoid Robotics, co-founder of Singapore-China Association Robotics Society of Singapore. In terms of scientific research, he has published 2 books, edited 2 books, over 10 patents of invention, over 30 research papers in scientific journals, and international conferences. Welcome, Doc. Put you to start with.
Okay, so I can take over. Okay, so good morning in Indian and good afternoon in Singapore. Okay, so let me share my PowerPoint file first. Okay. Right, so let me see, I just play. Okay, the network. Okay, so I hope every one of you see my sharing of the PowerPoint file, and
Yes,
in
we can see it. Yes.
can you see it?
Yes, we can see
Oh,
the
okay.
presentation.
So in the next 3 hours, so I'm going to share with you about the technical aspect and the application possibility with industrial robot. And I understand, okay, most of you are working in industry, and some of you may have related technical know-how in automation, manufacturing, and eventually with the manufacturing process and automated machine. And eventually it could be a robot, and some of you may have experience with robot. Since your background are not quite uniform, this is why. So I try to give an overview about the industrial robot so that every one of you may have some, to gain some knowledge and the insight into industrial robot. Just now, you see my short introduction, and here just highlight to you a little bit about my background. So you see, okay, I'm working in the area of robotics, And the AI is a recent textbook that I have published. So I'm also the editor-in-chief of the journal, etc. And this slide show you my research focus from basic research all the way to applied research. Okay, and this is one of the one of the most powerful robot that we have developed at the NTU. So from the picture, you can make a judgment about the complexity of this type of robot. Okay, and this video is a recent advanced robot. Then immediately you understand the current state of the art in robotics, and in future the human-like robot may work in production line, in manufacturing industry. Today, when we talk about the industrial robot, the main focus is on arm manipulator, but in future the arm manipulator can become a dual arm in the form of a human being. Okay, so for today's session, since we are going to have 3 hours together, so I will split today's session into 3 parts. So therefore, you may have gain the knowledge about the definition of today's robot and the major step involved in the design and the development of a robot. And the second takeaway is about the possible application domain in which we can deploy a robot. All right, and the interesting to you. And here I use this technical term, which is robot integrated manufacturing. I believe most of you may heard of this industrial 4.0. Then you may ask yourself, what is the nature of the industrial 4.0, and what will be industrial 5.0? Okay, so you can start to think about this question: what should be the next generation? Okay, to industrial 4.0, and if you start to think in this direction, then you may appreciate today's session, and later on we may have some discussion or Q&A. Okay, so let's start with the first part, which is for us to know, okay, what is the nature of a robot, what is the new definition of the robot, and what are the key steps involved in the design or development of the robot. All right. So first, look at the definition of the robot, and this slide shows you the world of life. Okay, and in which we see we have a lot of animal, and eventually we may find out the location for human being to involve. Then you may ask this question: why do we need to invent machine, to invent the tool in industry? The answer is what? The answer is to extend our physical capability and also to extend our mental capability. So if we enhance humans' physical capability by the use of a robot, therefore then you may ask the question, okay, how to position a robot today's robot can perform motion, and maybe tomorrow's robot may have a human-like intelligence. Maybe after tomorrow, robot may have life-like characteristics. Okay, then eventually we may put the robot inside this tree of life. Okay, so this is something for you to start to think. Then what is life from engineering point of view? Then the answer should be life is a complex system, which may include mechanic system, biologic system, chemical system, control system, information system, psychology system, and the intelligence system, etc. Okay, then based on this answer, then you can find out the characteristic of today's robot. Today's robot include mechanic system, include control system, include information system, include intelligence system. Okay, and we may have other machine which have a similar module, okay, or built-in module inside this system. Okay, then next question we may ask is will be, what are the limitations of a life in the world of the life, like animal and the human being? And even to human being, then we can identify these two major domains in which we can easily name some limitation. For example, for human being, okay, we cannot fly, John. We cannot okay dive deeper inside the water. Okay, so that is a limitation. That means we are limited in time, in space, in terms of the speed of the motion, and also for the payload for us to carry, we also have limitation. But in terms of knowledge, you may also see some limitation. For example, we may spend almost 20 years in school to study in order to get our PhD degree, master degree, or bachelor degree. That means it takes long time for us to acquire knowledge. Okay, and in order to process knowledge and perceive information, for example, our eye cannot perceive invisible light. Okay, and also about the language, and we can only understand or interpret the voice which are familiar to us. For example, if let's say I start to speak French now, and for those of you, if you do not understand French, then you cannot understand what I'm talking about. So that is limitation, John. So we have a limited capability to interpret the voice, etc. So you will see for life, we have a lot of limitation. Then how to overcome our limitation? Just now I already mentioned. So the universal way to overcome our limitation is to invent the tool and invent machine. Okay, then in this way, this tool, this machine can help us to extend our mental capability in terms of perception, processing, decision making, and also to extend our physical capability in terms of locomotion, grasping, and manipulation. Okay, so this is why we invent airplanes so that we can also fly. Okay, we have a robotic arm, therefore we can overcome our limited payload. Okay, because we can use robot to carry heavy payload. Okay, and in future maybe we can have a robot to assist us to study. Then in this way we can shorten our learning curve. Instead of spending almost 20 years to study in the school, can we shorten this cycle time from 20 years to 10 years or to 5 years? Okay, so that is motivation behind the invention of a tool and the machine. Then the good news is, among all these machines, one special type of machine are called as a robot. Okay, and in particular, we have a robot which could be deployed in industry. So therefore, it is interesting for us to know or to understand the capability of industrial robot. All right, okay. And then, okay, come to this question. Among all the inventions, okay, what should be the most powerful one? Okay, or if we do a little bit the analogy, okay, between invention or creature by the nature and the creature by human being. Okay, so everyone understand that the most advanced creature by the nature should be human being. Yes or no? It should not be elephant. Okay, we are smarter than elephant. Should not be the horse. Also, the horse can run very fast. Okay, but globally speaking, okay, so human beings are the most advanced creature by the nature. Okay, then among all the machine, okay, what should be the most advanced one created by human being? The answer should not be the airplane. Also, the airplane can fly in the sky. But in terms of complexity of the motion, the airplane only has, one airplane only has 6 degrees of freedom. There's a 3 translation, 3 rotation. But for the humanoid robot, for example, just now you see the robot which looks like a human being. Such a robot has at least 40 over degree of freedom, 40. Okay, so in terms of complexity of motion, humanoid robot is more complicated than an airplane. Okay, then in terms of perception, because for airplane fly in the sky, usually inside sky, the environment is quite simple. Okay, there may not be other obstacle there. Okay, but for humanoid robot work in a human-made environment, so the environment is very complicated. Okay, so in terms of perception capability, humanoid robot are more powerful than an airplane. So therefore, the answer is obvious to you. Okay, I believe every one of you will agree. Advanced robots are the most powerful machine on Earth, or are the most powerful machine invented by human being. Okay, because in terms of motion, robot can do locomotion, grasping, and manipulation. All these are human-like behavior. Okay, then in terms of intelligence, and now robot is trying to catch up with human-like intelligence. But today we are not yet there. Okay, but for those of you, if you follow the news in the media, then you understand that today a lot of interest in AI or deep learning or these kinds of research. And the intention is what? Intention is to let the machine or robot to catch up with human-like intelligence in terms of perception, decision making, and action taking. Right? Okay. So this slide help you to understand. Okay, this exciting type of machine. Okay, invented by human being. Okay. Now I just show you or quickly go through some typical application scenario in which we can make use of industrial robot or service robot. Okay, but I will come back again to industrial related application. And by seeing this picture immediately, you understand robot can help us to do the painting, and the robot can extend doctors' physical capability to undertake surgical operation in a very, very confined space. Okay, for example, inside the body of a human being. And also, robot can help us to extend our physical capability for building construction. So you will see human being just sit, okay, inside the control room. This is the indoor environment. Then the outdoor environment, we let the robot to do the job for us, because the outdoor environment could be humid, could be at the high temperature, okay, or noisy environment or dangerous environment, etc. therefore human beings just sit inside the control room, right? So and also we may deploy a human-like robot to perform some some performance and the demonstration, and eventually you can play the role of reception at a certain place or location or something like that. So based on the recent development of a robot, then we must redefine the definition of a robot. If you follow the old definition of the robot, then you may notice that the statement is not relevant to this robot, because the old definition basically follow the definition advanced by Robotics Association in USA. So that definition is suitable for industrial robot, but today's robot has already exceeded the capability of an industrial robot in the old day. Okay, so here I just highlight 3 key points inside the definition of today's robot. First key point is about the performance of a motion. So a robot must be able to automatically perform a motion. So this is the key point number 1. And the key point number 2 is for today's robot, must have this capability to interact and proactively to interact with a human being or human operator. Okay, so this is a key point number 2 inside the definition of today's robot. And the key point number 3 inside the definition of today's robot should be the capability to accomplish tasks. Okay, so these are the 3 important key points for today's robot to achieve in order to be qualified to be a robot. Okay, so then now we by now we understand what is the definition of the robot. Okay, so there are 3 key points inside the definition, and now we look a little bit the history of the robot. So if you look at the history in the past 1,000 years or 2,000 years, so you will see 500 years before the Christ, so it's almost 1,005 years ago, so you will see we have a invention made by human beings, by our ancestor. So you will see at that time people has this creativity of inventing human-like creature. Also, we do not have the actuation incorporated into these kinds of a creature, but at least this is the starting point for people to venture into the creation of a human-like creature, or machine, something like that. Then later on, people add in, the actuation of this creature in order to produce a motion. Then in this, so we have this bubble. So in this scenario, so you see the energy come from a human being. The human being's energy is being transferred into the mechanism of the creature, so that this machine can also undertake a motion. So this could be the starting point for our ancestor in the early year or early day to have such intention to invent human-like machine. But in the past 100 over years, less than 200 years, so this is the modern history of robotics. Then we need to remember 3 important events. The first one is about the birth of man robot. So then occur in year 1921. So this technical term robot was invented. Then second event about the inventor in 1941. then robotics term has been invented. Okay, so and the third one is about the birth of robotics industry. So what will be the first company in robotics which was set up? Okay, so the answer is this one. So in year 1956, so this is the first robotic company which was set up in USA. But actually before this, in okay, so people has already developed a teleoperated, but it has not yet been commercialized. It's not a commercial product. It's just a prototype. So the setup, okay, in robotics. So it occurs in year, okay, 1956. So this just give you, okay, the idea about these three important events in the modern history of robotics. Okay, so one was this term robot, okay, was invented, and the one was this term robotics was invented, and the one was the first robotics company has been set up, okay, in the world, etc. Okay, then it is interesting to know that if you look around the whole world, okay, which is the country that has put the most effort into the development of the robot? So the answer will be Japan. Okay, so it's not the US, it's USA or not Canada, it is not France or Germany or UK, etc. So actually, I believe it's Japan, which has put the most investment and the most effort into the development of a robot. If 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 let's say we ask you to name the top company which could sell industrial robot, so at least you could name two company from Japan. Sure, Motorman is one of it. Then there's another, Fanuc is the second company. So there's a Fanuc robot, and another is a Motorman. So these are the two leading company in the world which offer you industrial robot. Okay, then in Europe, you may have ABB from one company from Sweden. Then you have and another, previously we call it the Stobli. So it's from Germany, and in US, you may name the Adapt, just one company, China. Okay, but if you compare the strengths and the state of the art in terms of industrial robot, I believe the leader, the top three could be ABB and the Fanuc and the Motorman. Okay, so two of them are from Japan. Okay. Then besides that, the Honda is an automobile company. Actually, he has developed the most advanced humanoid robot, etc. Okay, so this slide basically highlights a little bit the short history, modern history of robotics in Japan. Okay, so you see this is a very interesting country, which has paid a lot of attention on the development and advance, okay, in robotics. And if we just look at the history of robotics from a single company, Honda is an automobile company, is a car maker. Actually, it's not the robotics company. Then you will see it has put a lot of effort in developing the most advanced robot, because the humanoid robot is more complicated than industrial robot. Okay, so then you will see in the world you cannot find a second company in general okay, for the overall performance. You do not have other company which can outperform okay, the Azimo, the robot developed by Honda. Also, the US company Boston Dynamics. Just now, at the beginning, you see the video. That humanoid robot was developed by Boston Dynamics, which is a USA company. But that robot only demonstrates the motion capability, but in terms of appearance and the other capability, they cannot outperform Asimo, the one developed by Honda. Okay, so then this slide basically show you what the capability of the humanoid robot by Honda. Okay, so that the overall performance, which involve manipulation and also okay, is vision, grasping, manipulation. And that based on this result, then you can start about what happens impact of a humanoid robot on industrial application. Okay, so you can start to think about it. Eventually, you may raise the question, but during the Q&A session, then we can discuss about this. Okay, all right. So then this slide basically give you another view about the history of robotics in terms of the prototype development, because we can classify robot into different type. For example, mobile robot, arm manipulator, industrial robot. Then you see the humanoid robot. Then in general, you may have a service robot. So actually, we have at least 4 major type of a robot, because service robot may cover the flying one, the swimming one, the diving one, etc. So all the rest we can lump them into here. Okay. Then mobile robot may include today's vehicle. That means actually today's car, we cannot name today's vehicle as a robot, because today's vehicle have not yet reached the level to perform a motion automatically or autonomously. Also, we have a lot of research in the direction of developing autonomous vehicle. But this is an effort to make today's vehicle to behave like a high-speed mobile robot. Okay, so now you see the importance of robotics, because we try to absorb automobile industry and make automobile industry to become a part of a robotics industry. And it's because of this, because a lot of technology developed in the area of a mobile robot, we can implant all this module or technology into today's vehicle that make today's vehicle to become a high-speed mobile robot. Okay, so you see the robot, okay, onto the industry. Then if we use all these 4 major type of robot as an example to look at the modern history of robotics, then you will notice, okay, so you will see for industrial robot, then the history started in year 1949. Why 1941? Is because in this year in France, there is the first prototype of a tele-operated robotic arm. So that prototype actually is the prototype of an industrial robot. Okay, so continuously evolving until today, and slowly these two emerge because we have looks like humanoid robot. All right. But in parallel, you see the humanoid robot started in year 1973 in Japan. It's Waseda University. Okay, this is the university which developed a humanoid robot in the early day. Okay, in the history. And in parallel as well, so you see for mobile robot, view the robot, and this history started in year 1961. And for service robot, okay, the big demand or intention or motivation is about the assistance to doctor. So we develop a robot to extend the medical doctor's physical capability so that we can do operation in a small, very confined area. Okay, so you see the history for these four major type of robot. Okay, and for this one is very interesting eventually. So vehicle move on the surface of the water. Okay, so you become part of this mobile robot. Okay, so that gives you idea about the importance of robotics in future, right? Okay, and then we dive a little bit into technical aspect of robot. Okay, then what will be exactly the detail of a robot? So just now we tell you the definition of the robot with the three key points. A robot is something which can perform motion. A robot is something which can interact with a human being. Robot is something which can perform a task. Okay, so let's just tell the capability. Then how could the robot produce motion? How could the robot interact with a human being? How could the robot perform a task? Okay, then this slide shows you the answer or technical solution which has been developed inside the industrial robot. From here, if you can understand this slide, basically you understand robotics already. Okay, and the list also highlights the major module involved in the detailed study of robotics. Okay, so first module is a motion planning. Second module is about kinematics, and the third module is about the dynamics of the robot, and the fourth module is about the robot control. Then we may have another module about the design of the robot body. Then we may also have an entire course about the AI or robot intelligence. Okay, so this gives you the big picture of robotics in terms of technical detail. Okay, so motion planning basically is to translate task description in the form of a human language into the motion in task space. Okay, so this is why we require robot to perform the motion. Then why do we need the kinematics? The answer is what? Because robot are integrated machine, so a lot of join or degree of freedom. Then we need to translate motion in task space into the motion in joint space. And this could be automatically done by kinematic equation, in particular inverse kinematics. So we have a solution. That means if you have a machine with n degree of freedom, this n could be any value, could be 100,000, does not matter. We have a solution, a matrix, okay, very big matrix. Then we can convert this into motion in joint space. So this is a magic result in robotics. Okay, then forward kinematic is just for us to verify whether the motion in joint space and match or correspond to the motion in task space or not. Okay, so this is about the motion planning, and the challenge we will come back at the part 3 to discuss about this. And for those of you, if you work on advanced robotics or if you are interested in with AI, then you may ask this question. Okay, could today's robot to automatically undertake motion planning, just take a task description as an input and do and produce motion as output, without the human intervention, you can start to think about this question. Okay, whether the answer is yes or no. Okay, if it's no, then what should be done? Okay, in terms of research, etc. Okay, then for robot control, this is not the challenge because today, once we know the design of the motion to be performed by robot, and in control theory, we have a lot of method to achieve closed loop control. You can use a PID controller or use a lead lag compensator. For those of you with knowledge about control theory, immediately you know PID controller and lead lag compensator. Okay, but we may have a little bit challenge here in terms of actuator, in terms of a sensor. So if we have a very powerful, how to produce very powerful actuator, that means which can deliver high torque as output. So then there's a limit there. Can we overcome such a limit to push the boundary? Okay, so here we may have some research to advance technology of actuator. But for sensor, also is accuracy and also to sense the force and the torque and the other type of motion parameter, and also in terms of accuracy and the resolution, etc. All right. And for this part, just now I asked you about the question: could today's robot automatically do this motion planning or not? The answer is no. Okay. And then you may ask this question: how come AI has been in place for 70 years, 70, and actually AI does not offer a very significant module to help today's robot. Actually, okay, and then you can ask this question: how come? The answer is what? Answer is here. If you can understand this slide, then you understand the answer immediately. The reason is what? The reason is that today's AI has an upside down history. So it's strange to you, John. You see, the first generation of AI actually aim at a very high level, okay, which is not grounded on the foundation of the AI. They just ignore the foundation, and people overturn this this theory, okay, just reject this. Let's say around this year, and then should not be the foundation of AI. Then we focus on development and learning. Okay, this is second generation until you see a lot of study focus attention on deep learning. This is not the answer. Okay, so this is why starting from the year 2000, we start to reject all this. What should be the true foundation of it? Then we have this upside down history. So that gives you the answer. How come? There's very little result we can use here to achieve of here. And this is why when you use industrial robot, and one tedious task is to teach the robot to perform your industrial task. Okay, so now you understand the answer already. So I give you the answer. So we advocate this in year 2009. That means robot intelligence must enter the third phase or third generation. In 8 years later, this is in year 2017, okay, 2017. So in China, they recognize, okay, we must enter new generation understand this slide. They do not understand generation has already been. We are still in the first generation. Then they put one generation behind today's state of the art. Okay, but in DARPA, this is the Ministry of Defense in USA. Actually, they understand. Okay, what we are talking about. Okay, so in year 2017, they also mentioned we are in the third wave of AI. Then DARPA, this is a slide from DARPA's presentation. Okay, so you can find in year 2017. So they made learning is absent. Okay, then second generation, then they put a lot of emphasis on learning, statistic learning or deep learning, etc. All right, and then they say this may not be the answer. They agree with us. Okay, then they say okay, something like that. More learning. Then you will see, okay, is 8 years behind us already. Okay, in year 2009, we already declare, okay, we enter the AI 3.0, okay, third wave of AI. Okay, so this is just for you to know. And this information is just for you to understand how come when you deploy industrial robot in your production line, at the beginning, you must spend a lot of effort to do the setup, to do the programming, or to teach the industrial robot what to do. Okay, now you understand it's because of the delay or delay of advance in AI. Okay, then what should be the blueprint of a robot intelligence or artificial intelligence? This is why we advance. Okay, in 2009. Okay, we do this today in the past 70 years, 70 in AI. Actually, we are doing this, but we believe we are doing this. That is the problem. Actually, we are doing this. We are not doing this. Okay, so and we are doing computer-aided intelligence. Okay, we are not doing robot intelligence. All right. Okay, so this is should be the blueprint for us to follow. And in this blueprint, and what is important is the role of language. Then how come we have this upside down history in AI or robot intelligence? It's because we misunderstood the role of language. And today you can still heard of this term, natural language processing. Immediately you understand. We consider language is a domain of application. That is wrong. Language is the enabler of AI or robot intelligence. Without the language, machine can never increase its level of intelligence. It's like human being. Without the knowing language, it's impossible for you to get your university degree, John. So it makes sense, all right? So what is the definition of the knowledge? So here we give you the definition. You can search in that because over 70 years, what is knowledge? Then you have a different kinds of answer, okay? And this is why, so we have very little progress in AI, okay? Now here I show you what are the 4 pillars which enable us to reach this level of true machine intelligence. So these are the 4 pillars, okay? So this is just for you to know, okay? Now I just quickly go through the procedure, okay, in order to design robot as a product. So this is a general guideline for us to design anything as a product, and we can also apply this procedure to guide us to design robot as a product. Okay, so then in this way, I believe because all of you are come from the industry, Then you can make a decision of buying robot, okay? Then to program the robot bought by you, then to automate your production line. You can make another decision of setting up an in-house team to develop a customized robot to meet your production line demand. Okay, then in this way, your in-house team can follow all this procedure to design and implement customized robot which meet the requirement of your production line. So you have two options. Okay, so I just show you this knowledge and this is the guideline. Then you can make these kinds of decision. Okay, so once you decide to have an in-house team to develop a customized version of your own robot in order to meet the demand of your own production line. Okay, then this is the idea you need to have. Okay, so robot basically is a machine which can perform the motion and also can perform a task. I can perform a task. He can carry the tool. If the tool is a welding gun, then he can do the welding. If the tool is a pen spraying machine, then you can do the painting, etc. Okay, and the robot is programmable so that this is a minimum interaction with a human being. That means the user operator can change the program at least. Then the robot can respond to the new program uploaded inside the robot. Okay, and since you can change the tool, change the program, okay, you can undertake different tasks. So this is why we call it as a multifunctional. Okay, then depends the level of a certain level of intelligence, etc. Okay, then once you are going to design your in-house version of a robot, then you need to have a team or sub-team, one to take care of a mechanism, the body of your robot, one team to design of a programming system of your robot, then another team to take care of kinematic, etc. So then you based on this blueprint, you can organize your in-house team into different subgroup already. Okay, then what are the minimum requirement for your in-house team? You can say, I cannot afford to have a full team to develop a product as like a commercial product, okay, with a complete feature. So these are the minimum group. Group and also take care of this actuation, and the one control group and the one programming software group. So to take care of the first two aspects, then control team or control group and the software group. Okay, so let's give you the answer. If you say you want to have an in-house team to build the in-house version of the robot, and in your in-house team, at least you must have a 3 group of engineers to work on this. Okay, then for your mechanic group, what should be their job scope? Their job scope is to design mechanism, and the second one is to take care of the actuation, to put in the actuator to power your robot's body. Okay, then what is mechanism? Actually, it's quite simple. It's the two basic building blocks are link and the join. Okay, so you have a link and the join. So it's very simple. Okay, and by combining the link and join together, and here you see 3 typical type of industrial robot. This is, we call it as an articulated robotic arm. That means every joint will provide rotary motion. This we call it as a scalar robot. So you see the first 3 joints are articulated joint, and the last one could be prismatic joint, that means undergo linear motion, give you the rotary motion. And this we call it a XYZ robot or Cartesian robot. This one give you 3 linear motion. So these are the 3 major type of industrial robot, okay, in manufacturing, okay. But of course, in future, I believe if let's say we replace or free human worker from production line, the best robot should be this one, John, because our intention is to free human worker from working in the production line. Then therefore, the human worker can just work in a control room or doing some service work, okay? So then the best version, okay, all right. So then second job scope is to provide the motion to actuate the mechanism, okay? So then in this case, okay, let me see, I just show the video because I need to off this one. Actuation means what? To make your to produce motion. And this is something for you to know, okay? And the conventional way to actuate a robotic arm is to insert motor actuator inside the joint, okay? Therefore, then this motor actuate this joint, then this joint will drive this link. I insert another motor here to drive this joint, then this joint design example is here. Let me just show you. This is an actual design example for you. Here, then this is the shaft of the joint, etc. Okay, and then one more example here. This is a scatter robot. But this is a real design. And for those of you the design background, then you okay this diagram. Okay, so you have bearing. This is a motor. Okay, etc. The guiding principle is quite straightforward. Okay, apply the guiding etc. Of the conventional. I just quickly go through. So this is just an example for you to know, okay, very actuation actually is not reliable. If one motor fail, the entire body fail, China. But in case of a human being, you can start to think, if I have a pain in one piece of my muscle, I can still move my arm, John. My entire arm will never fail, even I have some pain with one piece of my muscle. All right? But how come for today's robot, if one actuator fail, the entire arm will fail? Okay? So this is no good, John. So you remember this. Then is any solution to overcome this? The answer is yes, because this is an invention by us in year 2000, almost 20 years ago, John. So then we achieve a similar result of a human-like actuation. That means we can, instead of doing one-to-one coupling, that means insert one motor into one joint, okay? We can do one-to-many actuation. If we can do one-to-many, then we can put the two motor here. Each of these motor can couple to all these joints. Then in this case, only when two such motor fail, the entire arm will fail, China. If let's say we have a 6 motor here, drive a 6 joint, then only when all the 6 motor fail, then this arm will fail. Okay, so this is our solution. Okay, that we developed almost 20 years ago. Okay, so then here we just show you the prototype that we have developed. So inside here, let's. So you see one degraph, second degraph. So all this motion will share a single motor, okay? And this is the real prototype. Each arm we have freedom. Inside we only have a motor. We have a robot there, okay? So have developed 20 years ago. So we have a single motor here, and this arm has a 20 degree of freedom. All right. So that gives you the confidence about the mechanic reliability of an industrial robot. If really we want to achieve this reliability, so it's not an issue. So at least you can believe today's robot are very reliable in terms of motion execution. All right, okay, so that give you this confidence, okay? Then how's about the performance of a task? And the answer solution is quite straightforward. So at the end, at the hand of your robotic arm, you just attach different tools. If it's for polishing, if it's I polish the edge of this workpiece, then you attach one type of a tool. If you are going to do the welding, then you attach another type of a tool, etc. So therefore, by changing the tool, then you can, okay, let the robot to perform a different type of task, okay. But here we just show you the the autonomy for today's robot to achieve. This is just a typical example of a hand-eye coordination, and this behavior is fully autonomous, okay, which by the robot. And for you to know this level need to undertake hand-eye coordination. Okay. Control the motion accordingly. Okay. Then in terms of control hardware, if let's say your robot has a many feedback control loop, so actually for each feedback control loop, you have 3 basic building blocks. Okay, it's highlighted by this slide. So you must have, for example, you must have an actuator, you must have a sensor to provide the feedback, you must have a controller. So this is the one control loop. You have another control loop. You have another control loop. Therefore, you have a multiple control loop. And then if your robot has a many degree of freedom, therefore then the robot must have a powerful brain. Eventually, have a primary brain, secondary brain, like a human being's brain. Okay, so this is a hardware support for the control system design. Okay, so then the third team should be software team, because you are able to control the motion of the robot's body. Then the next question will be, what should be the desired motion here? Then this information must come from the task to be performed by your robot. Therefore, you must have a team which take care of the motion planning. All right. So just now I ask you to think about this question. Could today's robot take a task description as an input to automatically produce motion as output? The answer is no. Okay, this is what we want to achieve in future. Is we have a task description as an input, then let the robot to do this instead of operator, because today's robot cannot take this as an input because AI has not yet reached that level of achievement. Then what will be the solution? Then no choice. We must employ operator here. This is just for you to understand. Okay, when you deploy a robot in your production line, you need to spend time to do the setup, to do the programming, or to do the teaching, to teach your robot, okay, to perform the task. Okay, so it basically is this scenario. All right, now you understand, okay, what's going on when you buy a lot of robot to deploy in your production line. Then you see how come I must spend a lot of time to program each robot. Okay, so this slide help you to understand the answer already. Okay, and this video just show you example of okay, teach robot to follow specific motion. But robot can learn from humans' intention of the motion. So we can use our arm to the robot arm to move in specific. Okay, with such capability, then we can teach robot. This is an example to teach a robot to do welding. So you must tell the robot all the waypoint, okay, to go through. Okay, so at each waypoint, we call the waypoint. Okay. So all these are the key waypoint for to pass through. Okay, to go. And go the waypoint. Okay. Yeah. And next question you may ask yourself, how to shorten such a learning cycle? Because if I have to teach robot, okay, every detail of every motion, so it is time consuming. So could we, okay, increase the level of intelligence of today's robot and let the robot, okay, to understand my requirement? I just type a text, okay, to do this at what speed and the what location. I type the text, the task description, then I input to the robot, and that robot to understand my description, okay? So in order to do that, then we need to design a man, a robot man for robot. So then the two major functionality of a robotic man is to understand the meaning from a visual signal and understand. So this is a challenge for us, okay, to take. And today we are not yet there. Also, we more or less build up the new foundation, okay. So you can see that the real progress in AI maybe was started just 10 years ago, because before that we are going just remain still at this level, but this level is not the robot's true intelligence, it's just computer aided intelligence, okay. So and now you understand the reason, because it's only recently we start to venture into this direction, all right. So this is why today's robot, you should not put the very, very high expectation on its intelligence. Even for industrial robot, you should not have this expectation. Just buy a very smart industrial robot. And also with this knowledge, will make you to be vigilant. If the vendor approach you, tell you that my industrial robot is very smart, is very advanced, very intelligent, try to be careful, okay? So to be vigilant about the overclaim by your supplier, understand? So this slide help you to know, okay, to judge the level of intelligence of today's robot. So today we still need or require human being or human operator to assess or to assist industrial robot to learn, okay, the motion to be performed. All right, okay. And this is a result, okay. What we want to try to achieve to make a robot to understand human language, and this almost 15 years ago. So this is very old, 14 years ago. Okay, can you see? Okay. Okay, just now we stopped somewhere here. Okay, so from this short demonstration, and then you will see this will be the future expectation from the user of an industrial robot, and in future we will offer such a capability to the buyer of an industrial robot. But today we have not yet there. Okay, and this one also is the result of our development. Okay, so that means we can use a text or send the commands to the robot, and that robot to respond. Okay. Okay, so it's good enough. That means in future, now you understand, this is just to make you to understand, in future we want to achieve this type of intelligence for our robot. All right?
Recording stopped.
Okay, so we move on. Then you will see in DARPA, they also want to achieve a similar outcome that we have advocated more than 10 years ago.
Recording in progress.
So you see, this is a recent video, maybe 5 years ago, from DARPA. So this is the Ministry of Defense in the USA, and this is not the real result. It's just a film production. So and highlight their intention, okay, to make a robot of the future to be able to work together with a human being. Then the minimum requirement is for robot to understand description of the task. Okay, so therefore you see, so and our group and the DARPA, really we are at the front end of the development in robotics because we understand the same issue. Okay, and we are leading this development of robotics and towards the next level of intelligence. All right, okay. Then if they say, what is the current capability of today's robot in terms of intelligence? Just now I showed you a video with our humanoid robot to pick up the rapport. Okay, so I mentioned to you for hand-eye coordination, this has been solved. Okay, and here I highlight a little bit to you about this discovery of a human-like hand-eye coordination mechanism. What is the theory behind a biologic hand-eye coordination? So these are the results that we have discovered in 1997, almost 25 years ago. Okay, and this has been verified by US team in University of Pittsburgh in 2007. That means 15 years ago. Just verify this biological hand-eye coordination with the monkey. So you see the monkey's hand is here. And we use monkey's eye, monkey's brain to get the signal to control this robotic arm. Then use that constant matrix, okay, to get the data X, data Y, data Z. So this is a verification of this hand-eye coordination algorithm, okay. So that confirm, okay. So we can make today's robot to do human-like hand-eye coordination. So this is today's level of intelligence which could be reached by today's robot. But what we want to reach is to make a future robot to understand task description written in human language. All right. So that is the of development for robot intelligence. All right. So let me move on. Okay, so that's about the part one of today's session. Okay, so by now, if we just look at this summary for key takeaway, so now you understand if people ask you what is a robot, okay, then at least you can reply with these three key points. A robot is a machine which could perform a motion. Robot is a machine which could proactively interact with the people. Robot is a machine which could perform a task because robot can carry different tools. And also you know a little bit about the history of robotics, okay? And you know that Japan is a very particular country with a lot of investment in the development of robotics. And also you know, okay, in order to create an in-house team to develop in-house version of a robot for your production line, you must have at least three group of engineers. One group take care of mechanic design, another group take care of control implementation, and the third group take care of the software development. Okay, so that is a key takeaway number one for this sessions part one. Okay, maybe we take a break of 10 minutes, then we start at 2:05. Okay, so we take a short break of 10 minutes, then we start at 2:05.
Sure, Professor.
Yeah.
Thank you so much. Participants, I request you to not leave the meeting room. Kindly be in the meeting room. Just put your audios on mute and your videos off. We will reconvene in the next 10 minutes. That is at 11:36 sharp. Thank you. I request you all to be in the meeting room. Do not leave the meeting room. We'll reconvene in the next 10 minutes. Thank you so much.
Recording stopped.